Hi all, I'm Tom Sang. Our paper is called Parallel Structural Graph Clustering and its Approximation. This is joint work with Lakshman Dhulipala and Julian Shun. Graphs are a common way to represent data. A useful operation for more easily interpreting graphs is to identify clusters of closely related vertices. For example, we might cluster the graph on this slide in this manner. Usually we're looking for clusterings where most edges fall within clusters rather than between clusters. Applications of graph clustering include social and biological network analysis, graph visualization, and data partitioning for distributed processing. The focus of this talk is a particular popular graph clustering algorithm called SCAN, introduced in 2007. SCAN stands for Structural Clustering Algorithm for Networks, and it's analogous to the popular point clustering algorithm dbSCAN. The graph here shows an example output of SCAN. We'll describe SCAN in more detail later. In short, SCAN computes similarity scores between neighboring vertices and then uses two user parameters to determine how to group similar vertices into clusters. The problem with SCAN is that it has trouble scaling up to large graphs. Many modern graphs are extremely large with hundreds of billions of edges. Moreover, some graphs, like biological networks, can be dense, and SCAN struggles on dense graphs. SCAN has two bottlenecks. First, computing vertex similarities takes a long time, and second, tuning the two user parameters is costly. Though researchers have developed many variants of SCAN, none of them address both of these issues simultaneously. To address the first issue, some SCAN variants have used parallelism, as well as heuristics to prune out unnecessary similarity computations. To address the second issue, there are sequential SCAN variants that compute an index from which it's quick to compute clusterings given any parameter settings. Our contribution is to make SCAN feasible for large graphs by addressing both bottlenecks simultaneously, combining the ideas of parallelism and building an index. We parallelize an existing index-based SCAN algorithm called GS* index. Our parallel algorithm achieves strong running time bounds. It runs in logarithmic parallel running time, a big improvement in the parallel domain, and its sequential running time matches that of GS* index. We also show how we can use locality-sensitive hashing to develop an approximate, even faster version of SCAN that still has behavior close to that of exact SCAN. Finally, we implement our exact and approximate algorithms, describe optimizations to make our implementations run fast, and demonstrate that our algorithms are significantly faster than state-of-the-art alternatives on large, real-world graphs. For instance, on a 48-core machine, we saw a 50 to 151 times speedup on index construction compared to GS* index. For the rest of the talk, I'm first going to give some additional background about SCAN, then I'll talk about our contributions in more detail. Let's first define two terms, work and span, that we'll use to talk about running time bounds. The work of an algorithm is the sequential running time of the algorithm. It's the time to run the algorithm on a single processor. The span or depth of an algorithm is the parallel running time of the algorithm, the time to run the algorithm on unlimited processors. The ideal for a parallel algorithm is to get low span while getting work that matches the work of sequential algorithms for the same problem. Now let's discuss SCAN. SCAN computes vertex similarities and uses those similarities to compute clusters. We'll start by looking at the similarity computation. A pair of adjacent vertices is considered similar if they share a large proportion of neighbors. The original SCAN paper uses cosine similarity to measure similarity. On the slide is the equation for the cosine similarity between two vertices u and v. The numerator is the number of shared neighbors of u and v, and the denominator is the geometric mean of how many neighbors u and v have. As an example, let's compute a similarity between vertices f and g on this graph on the slide. Following the convention from the original SCAN paper that a vertex counts as a neighbor of itself, f has 4 neighbors. G also has 4 neighbors. The shared neighbors are these 3 vertices. Set that into the equation and you get a cosine similarity of 0.75. As a comparison, vertices D and E are less similar and vertices B and D are more similar. The cosine similarity is the traditional similarity measure for SCAN, but we also consider a couple other similarity measures in our work, namely Jacquard similarity as well as weighted cosine similarity, allowing SCAN to be used on weighted graphs. With the similarities defined, we can get clusters. Two user parameters control the clustering behavior, a positive integer mu and a similarity threshold epsilon between 0 and 1. Clusters are formed by finding vertices that have many similar neighbors and then clumping connected groups of those vertices into a cluster. What we mean by a vertex having many similar neighbors is that the vertex has at least mu adjacent vertices that are at least epsilon similar to it. But don't worry too much about this exact definition for this talk. That's a quick summary of how SCAN works. More precise details are in our paper or the original paper on SCAN. For the running time of SCAN, here we use m to denote the number of edges in the input graph, and we use alpha to denote the input graph's arboricity, a measure of the graph's density. The work of the original sequential SCAN algorithm just described is O of m times the arboricity, which is upper bounded by m to the 1.5. That's especially a lot of work for dense graphs. The expensive part is similarity computation. That takes O of m times arboricity time by itself. The subsequent computation to compute the actual clustering is a modified breadth-first search and takes O of m time. Our work is based upon an index-based variant of SCAN called GS star index. What does index-based mean here? Some variants of SCAN will interleave computing vertex similarities with computing the clusters themselves. This index-based variant of SCAN instead makes a hard separation. First, it computes the vertex similarities and constructs an index. Then we can query the index with any values of the user parameters mu and epsilon to get clusters. The index for GS star index consists of sorted lists of vertices that make it easy to find highly similar vertices. Then extracting a clustering from the index is quick, and users can tune the user parameters easily. We give a more detailed description of GS star index in our paper, or of course you can refer to the original GS star index paper by Wen et al. GS star index's main flaw is that it's sequential. The expensive vertex similarity computation for the index is still too slow, taking minutes to hours to compute on graphs with a billion edges. Let n be the number of vertices in the input graph. The work to compute the index is O of arboricity times log n, all times m. This is the running time of SCAN, plus an m times log n term that comes from sorting when computing the index. The work to compute clusterings from the index is at most O of m, but is typically much less since GS star index doesn't do any work to look at edges between insufficiently similar vertices. That's it for the background. Now let's talk about how we build a faster SCAN algorithm by adding parallelism to GS star index. The running time bounds we achieve are that our work bounds match that of GS star index, and we get lots of parallelism with logarithmic span. In fact, we can improve on the work bounds of GS star index. For unweighted graphs, we can achieve lower work for index construction using integer sort, and for dense graphs, we achieve lower work with parallel matrix multiplication. Beyond these provable running time bounds, we also describe how to implement the algorithm to make it run quickly in practice. First, we focus on the expensive similarity computation. I didn't discuss in previous slides how exactly to compute similarities to achieve O of m times arboricity running time, but one way that lends itself easily to parallelism is to use hash tables. Before computing similarities, make a hash table for each vertex containing the vertex's neighbors. The similarity between, say, vertices f and g on this graph on the slide is the proportion of neighbors they have in common. We can count the number of neighbors f and g have in common by taking the vertex with fewer neighbors, in this case either one, and looking up each neighbor in the other vertex's hash table. Doing this over all pairs of vertices gives the O of m times arboricity running time. That's a simple way to get the desired running time bounds, but for practical performance, we can do better than hash tables. Computing vertex similarities boils down to counting neighbors. That's the same as counting triangles. Finding that H is a shared neighbor of f and g is the same as finding that FGH is a triangle containing the edge FG. This observation is useful because now we can use optimizations from past work on fast triangle counting. One optimization is to direct edges towards higher degree vertices and only look for triangles of a particular orientation so that we only look at each triangle once instead of 3 times. Another optimization is that instead of hash tables, we get better caching behavior if we pre-sort every vertex's list of neighbors and intersect them to look for shared neighbors. For dense graphs, another trick is matrix multiplication for counting triangles. If we square the input graph's adjacency matrix, then the number of shared neighbors between vertices f and g is the row f column g entry of the result. This works well in practice on really dense graphs, and if you use fancy theoretical algorithms, you can get better running time bounds too. It replaces the m times arboricity work term with the work it takes to multiply two matrices in logarithmic span. Next, how do we compute the rest of the index? The index consists of specially sorted lists of vertices. Computing this in parallel works fine if we plug in a fast parallel sorting algorithm and do some doubling search in place of sequential search. An additional observation that isn't in the GSStar index paper is that instead of a comparison sort, we can actually use integer sort for unweighted cosine similarity and Jacquard similarity. The sorts are keyed on similarities, not integers, but it turns out that we can transform the inputs and combine arrays so that integer sort works out. This lets us drop the log n factor in the index construction work and replace it with a log n factor, or we can drop the factor altogether in exchange for boosting span to a small polynomial in n. Now we can query for clusters from the index. Skipping over many details, here we use doubling search to extract highly similar vertices from the index, and then we use a parallel connectivity algorithm to cluster the vertices. In practice, we use concurrent union find to compute connectivity with low overhead. This exact scan algorithm is already quite fast, but we have an approximate version of this algorithm that achieves further speedup. We target the most expensive part of the algorithm, the similarity computation, for approximation. Everything else works the same. The observation here is that we can use locality-sensitive hashing to approximate vertex similarities. Locality-sensitive hashing is a way to approximate the similarity between large sets. It works by mapping sets to smaller sketches that are quicker to compare than the original sets themselves. For us, our large sets are the neighborhoods of each vertex. Remember that the similarity between two vertices is usually defined as the cosine similarity of their neighborhoods. Then we can use SIMHASH, a locality-sensitive hashing scheme for approximating cosine similarity. For Jacquard similarity, we can use MinHash. The sample size k tunes the approximation quality. Higher sample sizes mean more accuracy, but also more running time. The running time benefit of locality-sensitive hashing is that in the work bound, we knock out the arboricity term and replace it with a sample size, lowering the running time on dense graphs. The span is still logarithmic. Moreover, we prove that the behavior resembles exact scan. When running scan, we only care about whether similarities fall above or below the user parameter epsilon. By applying concentration bounds to the random variables generated by locality-sensitive hashing, we can show that for a large enough sample size, we correctly classify all edges as above or below epsilon in similarity, except for a small interval around epsilon. In practice, we don't want to use locality-sensitive hashing everywhere. It helps for vertices with large neighborhoods, but for vertices whose neighborhoods are small relative to the sample size, we might as well compute similarities exactly. The optimization here is to apply locality-sensitive hashing on high-degree vertices and to use triangle counting to compute exact similarities elsewhere. That's an overview of our algorithms and the running time bounds. Finally, let's see our experimental results. We run our experiments on an Amazon EC2 machine with 48 cores plus two-way hyperthreading for a maximum of 96 simultaneous threads. The machine has about 200 gigabytes of RAM, enough RAM to process graphs with billions of edges without any compression. We compare our algorithm against GSStar index. We also want to compare against another parallel scan variant, so we compare against PPScan. The 2018 paper for PPScan compared it against other scan variants and found PPScan to be the fastest. We tested on 6 large real-world graphs. To reduce clutter on these slides, we're only going to show plots for the Fenster graph, the largest social graph we tested on, and the Cochlea graph, the largest biological graph we tested on. GSStar index and PPScan only run on unweighted graphs, so those algorithms will be missing on the plots for weighted graphs like the Cochlea graph. For index construction, we achieved a 50 to 151 times speedup versus GSStar index. Even when we run our algorithm sequentially, we achieve a 1.4 to 2.2 times speedup versus GSStar index thanks to the triangle counting optimizations that we have. Those times are without matrix multiplication, but if we use matrix multiplication on very dense graphs like the Cochlea graph, we get even more speedup. We don't have a comparison against GSStar index on the Cochlea graph because GSStar index doesn't run on weighted graphs. If we were able to run GSStar index, though, we'd likely have our algorithm using matrix multiplication demonstrating a 1000 times speedup. We time getting clusters by fixing one of the two user parameters and sweeping over the other, measuring clustering time at each point. Here we see a 5 to 32 times speedup versus GSStar index. We're also always faster than PPScan, though since PPScan is not index-based, a fairer comparison should include our index construction time. If we query clusterings at enough parameter settings, then our algorithm outperforms PPScan. For example, with our algorithm, if we sum the index construction time per fenster plus the time to query the 9 points on the plot on the slide, then our algorithm is faster than the time for pp-scan to query the same 9 points over fenster. The summary for the approximate version of our algorithm is that if we pick the sample size properly, we can cut index construction time in about half on several graphs while getting similar clustering quality to exact scan. The plot here displays the trade-off curve as we vary the sample size. We can get faster index construction time, the points towards the left side of the plot, but if we go too far left, then the clustering quality on the y-axis degrades. To conclude, we presented exact and approximate scan algorithms that beat the state-of-the-art and that scale to large graphs. We speed up the expensive similarity computation of scan with parallelism, triangle counting optimizations, and locality-sensitive hashing. The scan index, borrowed from GS*index, lets users quickly explore settings of the scan user parameters. We have good provable running time bounds, as well as an implementation that runs quickly in practice. Our code is available on GitHub. Possible future work here. First, the GS*index paper handled dynamic edge insertion and deletion to the index. Maybe we could parallelize this part too, achieving speedup by batching together edge updates and processing them all at once. Second, increasing the user parameter epsilon gives finer and finer clusters, so we could use a fast index-based scan algorithm to extract hierarchical clusterings quickly. Okay, that's all for this talk. Thanks for your time.